Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. We are on chapter 12, part 3. Okay, we're going to do an example. The book Small Data Sets reports on the article by Kadelia, Testing for Independence of Regression Disturbances from Econometrica, volume 38, pages 97 through 117. This article contains information on ice cream consumption over 30 40-week periods from March through July. The researchers were interested in determining what explanatory variables impacted the level of consumption. The variables considered in the study are Y, ice cream consumption, in pints per capita, X1, the price of ice cream, dollars per pint, X2, weekly family income in dollars, X3, the mean temperature in degrees Fahrenheit. All right, we have the model Y equals beta 0 plus beta 1 X1 plus beta 2 X2 plus beta 3 X3 plus epsilon. We're going to determine whether the price of ice cream, weekly family income, and the mean temperature together have statistically significant predictive value on the ice cream consumption. We're going to fill in this following Anova table. So we are conducting an overall F test because we're asking, do these three variables taken together, the price of the ice cream, the weekly family income, and the mean temperature in degrees Fahrenheit, predict ice cream consumption in pints per capita? All right, to fill in this regression table or Anova table, we start with the source. Okay, the degrees of freedom for regression. Remember, that's K. In this case, K equals 3. We have a total of 4 coefficients that we're estimating, K plus 1, and then subtract 1 to get the degrees of freedom. So we get 4 minus 1 equals 3. Our sum of squares due to regression given here is 0.0903. So if we want to calculate the mean square due to regression, we're going to take this 0.0903 and divide by 3. All right, so we get our mean squares due to regression as 0.0301. All right, our sum of squares due to error. We get n minus k plus 1. In this case, our sum of squares total, we do n minus 1. We're going to get 29 in this case. Now, altogether, this has to add up to the degrees of freedom due to regression, the degrees of freedom due to error, have to add up to the degrees of freedom of the overall total. So in this case, we can see that we get a value of 26 because 26 plus 3 is 29. Now let's just double check. What is n minus k plus 1? In this case, our n is 30, right? Our k is 3 for our 3 predictors, plus 1 because that's the y-intercept. So we get 30 minus 4. That's going to equal our 26. So n minus k plus 1, that was our denominator degrees of freedom, that's 26. Or you could have recognized that all 3 of these, this degrees of freedom due to regression plus the degrees of freedom due to error has to add up to equal the degrees of freedom of the total. All right, to calculate our sum of squares error, we can take our sum of squares total and subtract our sum of squares due to regression, and we're going to get 0.0352. All right, to get our mean squared error, we're going to divide our sum of squared error by our degrees of freedom due to the error, and our mean squared error is going to be 0.0014. To get our F test statistic, we're going to take our mean square due to regression divided by our mean squared error. We're going to get a total value of 22.23. And to calculate our p-value, we're going to get the area that is greater than that 22.23. And we get a value that's approximately equal to 0, right? So you can see here, we found the p-value by using PF, that's saying find the probability under the F distribution that our F statistic takes a value greater than or equal to 22.23, and that's Oh, lots of zeros, 2. So if we round off, that's approximately 0. All right, so our null and alternative hypothesis for the overall F test, we're saying beta 1 equals beta 2 equals beta 3 equal to 0. HA, at least one of the beta J's does not equal 0. So at least one of those slopes is different than 0. Okay, our test statistic, right? Our F test statistic is equal to SSR divided by the degrees of freedom due to regression divided by SSE divided by the degrees of freedom due to the error. This is equal to the mean squared due to regression divided by the mean squared error. In our case, 0.0301 divided by 0.0014, and we get a value of 22.23. All right, if HO is true, what is the distribution of our S statistic? Okay, if HO is true, right, then our test statistic follows an F distribution where the degrees of freedom 1 is equal to 3, degrees of freedom 2 is equal to 26, right? Okay, if we draw a picture of the distribution, here's what we get. Our F critical value, right? So if all of this area here, we set up to be equal to 0.05, we can calculate the F critical value to be 2.975154. Okay, we're going to just round that to be 2.98. All right, so essentially we asked and used the QF, which says, tell me the critical value under the F distribution where the area to the right is 0.05, the degrees of freedom 1 is K, degrees of freedom 2 is N minus K plus 1. Give me that upper tail, being 0.05 in the upper tail. All right, you can also use a table to get this critical value if you prefer. Our test statistic was 22.23, so that is way out here, right? Way out here. And this is the p-value, right? That's approximately equal to 0. All right, so overall, this is our test statistic. Our test statistic was beyond the critical value, and our p-value was much smaller than alpha. So our p-value is less than 0.001. Whenever we have a very small p-value, we can just bound it with 0.001. Okay, we can say since the p-value is less than 0.001, right? Which is clearly less than alpha, right? We reject HO, right? So at least one of the beta J's is different than 0. So what we can say is if we want to predict ice cream consumption, right? Then we can say the price of ice cream, weekly family income, and the mean temperature all taken together is predictive of ice cream consumption. So let's write that out again, right? So we say the price of the ice cream weekly family income and the average temperature, right? If it's hot outside, taken together are predictive of ice cream consumption. Okay, great. So essentially here, what we're saying is that if we want to predict how much ice cream people are going to eat, so we don't make too much ice cream, we don't make too little ice cream, we just make the right amount. Well, if we know what we're charging for the ice cream, we know how much people are making in the area, and we know how hot it's going to be outside, then we should know how much ice cream people are going to consume, which is great because then we don't make too little and not have enough to make enough sales. We don't make too much where we're throwing ice cream away.